We're going to move on to the nervous system. So we're going into body systems starting today. So it will be going at rocket speed. So I need you guys to, but that simply means that the material will not be too deep. It's going to be pretty on the surface. Okay, so it's not the depth part of it. We're not going to really hit until maybe we hit the cardiovascular system, okay? That's when we start really going back into depth. But this is all pretty deep, so you get this. So we're going to be surveying the nervous system, okay? Mainly because most of what's happening with the nervous system, we really don't know how it's happening. It's all a black box, right? So it's all, your guess is as good as mine. Okay, all right. So I would like to wrap potentials up with a discussion of graded potentials. So we're going to talk about graded potentials, and then we're going to move on to the nervous system. I'm really hoping to get some neurotransmitter mechanisms in today. And with that, most likely we'll get done with lecture. And then Thursday, we're definitely hitting the brain. Okay, so we will start the brain on Thursday. All right, so graded potentials it is. Here we go. So so I'll teach you this how I learned it as a student a while ago. Looks like I have to be careful when I say that. So when I learned this as a student, the trick I used, and I passed this on to my high schoolers who really liked it, which means that it's definitely a good way of learning. When you take an exam, your grade depends on how many questions you get correct, yes?
Yes.
Any test, right? So you take T's or NCLEX or whatever. Your score depends on how many questions you get right. Well, some tests may also depend on how many you get wrong when there's a penalty, right? But mostly, the more questions you get right, the better your score. Are you seeing that relationship?
Yes.
So that's how graded potentials are. They're graded because their magnitude depends on the magnitude of the stimulus. So these are voltage changes in a cell. That's always the case. It's always in a cell, right? Why else do we care? Right? We don't care about voltage changes in a battery, right? We're talking about living cells. So voltage changes in a cell, okay, where the stimulus intensity determines the potential strength. Right off the bat, tell me, is this all or none?
No.
Stimulus strength determines your intensity of the graded potential, correct?
Mm-hmm.
So is this all or none? No, because clearly there's a gray area, right? It's not black and white. Action potentials were black and white. If you hit threshold, action potentials are unpreventable. They will go through. Clear?
Mm-hmm.
But graded potentials are not like that. Graded potentials clearly reflect the strength of the stimulus. Now, philosophically, if you think about this, it's really, really important. When you're responding to stimuli, the intensity of the stimulus is really important, right? I'll give you a very glaring example, right? Let's say that, somebody throws a little pebble at you, right? You get annoyed and you go, what's wrong with you, right? Or something, and you move on. But if I were to, project a huge boulder onto your face, that is not going to be a reaction. I hope not, right? Clearly, they're both rocks, right? You can't argue that, right? You can't say that one is threatening your life and one's, not going to affect you at all. It's just irritating. Am I making sense? Mm-hmm. So stimuli are like that. You can have a stimulus that is really weak and not very, not very affecting you in any big way. But then again, you can have stimuli that are huge. That can be life-threatening, right? So you need to be able to respond to both, right? if you have a little kitty cat run at you versus a big lion running at you, there's going to be a difference in how you respond, right? It's the same type of idea. So graded potentials, please understand, and this is the most important statement here, sensory receptors, and understand that sensory receptors are mostly cells, okay? Sensory receptors undergo graded potentials. Okay? So what then happens is if the graded potentials, okay, are strong enough to open voltage gated channels, hello, there it is. Okay, threshold will be reached, and therefore what will happen? That's right. So let me summarize this for you. This is a really, really important idea. Okay. First of all, the fact that sensory potentials are graded potentials. Second of all, I want to mention that if the graded potentials are strong enough to open voltage-gated sodium channels, action potential can be generated. This is crucial. Okay, so make sure you know this. This is the working principle of many, many different systems that we'll be going through. So the bottom line is this. So you have a stimulus. So if you have a strong stimulus, okay, if you have a strong stimulus, this will lead to an equally strong graded potential, GP. GP is graded potential, okay? That simply means it's too late in the afternoon. And if this is strong enough, then what happens? Voltage-gated sodium channels open, right?
Yes.
Guys, graded potential is a voltage change, correct?
Yes.
Any potential, the word potential means a change in voltage because ions are moving.
Yes.
So graded potential becomes the stimulus for voltage-gated sodium channels to open. Do you understand?
Yes.
You already saw that in action potentials, right? So look at this graph. Remember this graph?
Yes.
All too well, right? Memory burns. So what happened here? You're at rest, right? So what happened exactly at this inflection point, at that turning point? What happened? Stimulus hit. Guess what that stimulus is?
Great.
Make sense?
Yes.
Are you connecting the pieces together now?
Mm-hmm.
Yeah.
Yes? No?
Yes.
Okay. So voltage-gated channels open and boom. If threshold is reached, if threshold, then AP. Right? If threshold, then AP. Okay? So if you hit threshold, then you hit action potential. So let's talk a little bit more about graded potentials and contrast them with action potentials. Just to review action potentials here also. All right. So here's graded. I'm going to use a different color. So let's say here's graded potentials, and let's put action potentials in red. First of all, and I'm doing a compare contrast. Okay. So first of all, graded potentials, ions flow, right?
Yes.
So voltage change, ions flow causing a voltage change. Do you agree? That's
Yes.
a bottom line, right?
Yes.
So what happens with action potentials? Same thing.
Yeah.
Ions flow and you have a voltage change. So that's a similarity. In both cases, ions are flowing.
Mm-hmm.
Okay, and you have a voltage change as a consequence. That hence the term potential. The word potential signifies that. Number one. Then number two, okay, for both graded potentials and action potentials, you're going to need IMPs, correct?
Yes.
Without integral membrane proteins, can ions flow?
No.
Okay, bingo. Okay. Now, with graded potential, we're going to start seeing some differences. Graded potential can be, oops, wrong color. Okay, can be depolarizing, which means what? What's depolarizing? Change. I don't want to hear the word change. That is the most generic statement. Be specific in your answers. What is depolarization?
The cell becoming positive.
Cell becoming positive. Correct? True or false? Only sodium can depolarize the cell.
False.
False. You will learn in the heart that calcium depolarizes pacemaker cells. Okay? Number one, in the ears have never heard of sodium. You don't have sodium here at all. Okay? It's all potassium. Okay? So, to my knowledge, ears don't have a sodium potassium ATPase. They don't need it. Okay? It's all potassium, potassium, potassium. Pancreas, okay? Insulin secretion, that's all potassium. Okay? So please understand that it's not always sodium. Okay? Most of the places it is. Okay? So it can be depolarizing, meaning the cell becomes more positive, correct? Or hyperpolarizing. Why didn't I say repolarizing? So go back to definition. Whenever I throw a curveball like this, stop, ground yourself and say, I can do this. What is hyperpolarization? Let me think about it. What is hyperpolarization? So tell me, what is hyperpolarization? Too much negative. Fantastic. Too much negative inside the cell, right?
Yes.
So too much negative. Question is, so what's the difference between hyperpolarization and repolarization? Exactly. Thank you. Repolarization is coming from amplitude, correct?
Yes.
Hyperpolarization will be coming from rest. It will be coming from rest. In action potential also, it's coming from rest. You have to hit rest before you hyperpolarize. Do you agree?
Yes.
So, let me explain this a little bit more. So, depolarization happens when sodium channels open, correct?
Mm-hmm.
Yes.
And you have sodium influx. What about hyperpolarization? The easiest one.
K plus.
Potassium, good. Potassium channels open. And these are all voltage gated channels, by the way. Well, no, I take that back. Wrong, wrong, wrong. Erase, erase, erase. I should be shot. No. So, not at all. In fact, they're not voltage gated channels. In fact, okay, so no. What am I thinking? I should retire. Potassium channels open. Okay? So, what will potassium do? If you open potassium, with the exception of the ear, because in the ear, when you open potassium channels, potassium goes in. Okay, it's the only place where potassium influxes is your cochlea and your semicircular canals. Okay, nowhere else has that happened. In the rest of the body, if I open potassium channels, what will potassium do?
Leave.
Effluxes. Okay, you got to become Queen of England. Come on, victorious! Everybody, use bougie language. Effluxes. Potassium effluxes. Okay, if you can read that. Okay, effluxes. If you're at rest, -70, right, and potassium starts effluxing, what are you going to do? Are you going to dip or are you going to rise? Dip, hyperpolarization. Do you understand?
Yes.
And so here's the most important difference. These are not voltage gated channels. Extremely important. They're not voltage gated. Think about it. If these were voltage gated channels, can this be a big spectrum or will it be all or none? If you use voltage gated channels, can you get an array of responses or is it going to be, that's it, I hit threshold, boom? The second one, right?
Mm-hmm.
So voltage gated channels can only give you action potentials. Note that down. Extremely important point. Voltage gated channels can only generate action potentials. Are we clear?
Yes.
So these cannot be voltage gated. Okay? So some more pointers for action potentials. This is a cycle of events, okay? Greater potential is not a cycle, okay? So it's a cycle of voltage events, right? And repolarization, unique to action potentials, correct?
Yes.
So in good old days, namely 2021 and before, you had to write essays like this. I would ask you to compare action potential to greater potential. Give me 5 similarities and 10 differences. On the spot, you had to come up with all this. Look at what the class has become. Multiple choice. Okay? So wonderful improvement. But the point is, I still want to impart to you how to learn this, right? Just because my tests have become laughable doesn't mean you can't learn. Okay? I'm still going to present you with these things. And unfortunately, the rest of the world doesn't care for essays and technical writing in science. Okay? It's not just us. No one really cares. Nursing school doesn't care. They're like, we don't care, you know, if you put this on. In fact, they don't want us to put writing on exams because nursing exams don't have writing. Okay? They only have tough multiple choice. So they want tough multiple choice. Hello?
Yes.
Okay. Just checking if you're here. I'm not. Here we go. So repolarization is unique to action potentials. Okay? You will not see that in greater potentials. Okay. And then action potential is all or none. Okay? So you do not show any gray area. Okay? And this is very interesting. Action potential is initiated by depolarization. Correct? So action potentials usually depend on greater potentials. And I showed you how, right? Right there on top. So usually depend on greater potentials. And this makes another very interesting and important point, particularly for the nervous system. Graded potentials, okay, can typically summate. And that's a fancy word to say they can add. Voltage is just a number, right? It can add. Okay? Action potentials is all or none. Cannot add. Cannot summate. Okay? Because it's all or none. You cannot add them, right? How can you add them? They're all 100%, right? So in greater potentials, individual potentials matter. In action potentials, it's the frequency that matters. Big time. In action potential, frequency matters, right? So when I'm looking at you, okay, the image that's being formed in my eye, right, in this lecture hall, right, will have a certain frequency of action potentials going along my optic nerve to the brain. And the brain reads that and says, you're sitting in front of these students and you're lecturing. This is a lecture session. You're talking about greater potentials. Get your act together, right? Versus you were sitting in lab, right? We all had the EEG equipment out, right? And so there, it was probably a different frequency of action potentials, correct? And today's lab, and Thursday's lab will get a whiff of this, but today's lab, you guys got an idea by looking at the brainwaves. So that's a reflection of this kind of stuff. Am I making sense?
Yes.
So, difference between graded and action potentials, very, very important concept, okay? Make sure you know this. I'm going to give you a minute to digest this and ask if you have any clarifications that you need. Again, I'm seeing that everyone's writing, that's great. I do give you these notes, but please write, because that's the way you learn. don't just sit there and stare at me. You will want to go to sleep. Okay?
Yes.
Sit there and write. Okay? If you write, you're learning. And that's 10 times better than staring at a piece of paper or the board. Okay? Yes, sir.
Could you explain a little bit more about how the individual potentials sign up for graded ones? Like,
We're going to see that in the rest of this lecture. So what I'm trying to say briefly though is, if I have a depolarizing signal and a hyperpolarizing signal coming simultaneously to a cell, okay, they'll cancel each other out. You can add them, right? You don't do that with action potentials, because they're all or none. It's either 0 or 1, right? What are you going to add? Either they don't exist, or you have a full action potential. Only if you have fraction of an action potential, you'll be able to add them, right? So by principle, by philosophy, you can tell that they don't add. Action potentials don't add. A stronger stimulus will send a more frequent action potential. That's the way it translates. Everybody see that?
Mm-hmm.
So thank you for that question. I'll write that down. So strong stimuli result in more frequent action potentials. That's a very, very important point. Are greater potentials clear?
So in contrast, strong stimuli make greater potentials more hyperpolarizing or depolarizing.
And remember that a stimulus can only generate one greater potential. Okay, whereas a given stimulus can produce multiple action potentials, right? Simultaneously. Okay, so that's the idea. So if you have a really strong stimulus, you'll produce a strong greater potential. Whereas a strong stimulus can produce many, many, many action potentials, and will produce many, 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 many action potentials. Clear? So, greater potentials can be produced in response to, okay, so GP can be produced in response to a variety of stimuli. You guys can read my writing, right?
Yeah.
If you can't, you have to tell me. Don't wait till end of the semester. Totally pointless. Okay, to a variety of stimuli. So what do I mean? Tasting sugar, right? Tasting salt, right? The more salt you put on your tongue, the saltier it tastes, right? Okay, so greater potentials. Pulling, pushing, right? Muscles, those are signals. So that's called mechanical stimuli. Blood pressure, right? Blood rushing through your arteries or blood rushing through your veins. That can serve as a stimulus, right? For the brain and saying, oh, blood pressure is, something's wrong with blood pressure here, right? So we need to correct it, okay, for example, right? If blood glucose is super high, right? You can generate, although that's not action potentials, but it's a similar idea. The more blood sugar you have, the more insulin comes out, right? And that comes out because of potassium-induced depolarization. So it is involving action potentials on some level, okay? But greater potentials, this is why I said sensory receptors. Anything that senses anything will involve greater potentials. Are we clear? Which will lead to action potentials, right? They're all connected, but one's not the same as the other. Okay, light, for example. When light hits your eye, you have a greater potential. Okay, it's actually a hyperpolarization. It's a greater potential, and you block sodium from coming in, and that will excite neurons to release neurotransmitters, which will then excite the optic nerve to send action potentials down the road to the brain. Okay, and that's how, we still don't know how the brain figures out what these images are. Am I making sense? We take, again, things we take for granted, right? Think about how does that exactly happen? Even better than that, as I'm looking at you, as my brain is thinking, I'm simultaneously talking. And all of you do that, right? When you have a conversation. as you think you're talking, you should always wonder, how the heck does that happen? Okay, because I always do. I always, if I pause for a second, I think, how did these words just come out? Okay? Particularly given that English is not my first language, right? So how do you habituate, and how does this happen automatically? That kind of curiosity really helps you learn. Okay, so keep that going. All right, so that's it for greater potentials. We're done with the potential part of this chapter. We're going to the next chapter. Yeah.
When you say great potentials can be produced in response to a variety of stimuli, for action potentials, does that mean that?
Thank you. Electrical only.
Okay.
That makes sense. Electrical only, right? Because the sodium channels and action potentials are, fill in the blank. Voltage gated. Thank you. If you're voltage gated, only voltage is going to open. What's voltage? Current. What's current? Electricity. What's electricity? Electrical, right? Okay, and we draw the world famous X. Okay, that means this chapter is over. We're starting a new chapter. Yay! Yay! And we're actually ahead. So, so this is going to be, okay, basically, even if not lying in Cancun, at least lying in the Oakland Bay. Okay, so this is going to be very, very on the surface. Okay, so nothing in depth. Okay. So we're going to the nervous system. I've already laid out all the foundations. Okay. So nervous physiology. Okay. And we will be proceeding to the brain and the spinal cord and all of that soon. All right. So the main job of nervous system, okay, the primary function, okay, of nervous system is homeostasis. Okay, and the most important word is rapid. Okay, nervous system is involved in rapid restoration of balance. Rapid restoration of balance. I'm going to say normalcy. Okay, so this is in sharp contrast with the endocrine system that's coming 2 chapters from, or maybe even I'll do endocrine, I don't know, check your syllabus. I think we have muscle and then we have endocrine. So in a couple of chapters, okay, so rapid restoration. Endocrine is very slow. Endocrine is very slow, okay, and some endocrine effects take years to finish. Puberty, for example, it takes forever, right? So nerve is not like that, it's rapid, okay? So neurons, okay, are the functional units of the nervous system. So remember, anything ending in on, O-N, again, if you took my anatomy, you know this. Anything ending in on, O-N, means unit. So neurons, unit of the nervous system. Okay. I have to do shameless advert. How many here need to take anatomy? Okay. So if you still like me by the end of the term, or can tolerate me by the end of the term, the plan is I'm going to be offering an 8-week anatomy course in the summer. And it's going to be live in person. Okay? So you guys get higher priority to sign up than high schoolers, right? But once that high school enrollment begins, that's it. It'll be gone in no time, okay? So high schoolers just want to take this kind of class because this gets them college credit, right? So they will want to do it. So if you're interested, I'm offering the anatomy. There's a lot of advantage to taking anatomy with me because you took physio with me, okay? Most schools prefer that you have the same teacher.
Yes.
That shows you're not teacher shopping for grades. Okay, anatomy, you can ask half this class, they took anatomy with me. I mean, even though there was a major curve, that class was not bad at all. Okay, I didn't, I felt like it wasn't that hard. It's a lot of memorization, right? But it wasn't that bad. But it is 8 weeks. okay, instead of 16 weeks. So you will be learning it, you'll be learning a lot in 1 week, right? So think of your time constraint and think of all your, whether you'll be able to commit that kind of time to the class and getting it done. I will not, and I promise you this, I am not teaching anatomy for the rest of the year. Okay? No fall, no spring. My schedule is already set. Okay, so I will not be doing that for the rest of the year. So in the academic year, you won't have me, you'll have somebody else. Okay, so if you want to take that class, summer is your chance to take it, because I want to try it. Teaching it in the summer. Okay? This summer, most likely after this summer, I won't teach anatomy at all. Okay? It'll be passed on to part-timers. Okay? So it doesn't excite me. So, I like physio so much better. Okay, back to fun. So neurons are functional, so that's my shameless advert. I'm also teaching the cancer bio class, which is fully online. Cancer bio is fun. That I'll teach every summer. Okay, so that's a lot of fun. Fully online, no prereqs. It's a great class for any medical career, right? Because it's medically oriented, right? And you'll apply everything you learn in this class in there. So if you've taken this class, cancer bio is going to be walk in the park. Okay, so highly recommend it if you want to take it. Again, that fills up with high schoolers a lot. Okay, even though the capacity is 30, so it's not like this class. So 2 classes in the summer if you can handle me. And in the cancer class, you never have to see my face. That's a selling point, right? You do have to hear this voice, but you never have to see my face. Easy enough. And that's also an 8-week class. No lab. There's no lab for cancer bio. Just lecture. Okay, it's a nice little elective. All right. Neurons are your functional units. Neuroglia. And I'm not going to go over all I'm just going to mention the neuroglia. You don't have to know all the huge details. That was covered in anatomy. I'm not going to cover that here. So the word glia means glue. So they are symbolically and physically acting like a glue, right? So how symbolically? They're supportive. They provide support. And 99% of neural cancers are neuroglial cancers. Okay, because they divide a lot. They get damaged a lot, they divide a lot. Okay? Neurons, for the most part, there are exceptions, neurons for the most part don't divide. They're terminally differentiated. Okay. All right. So neuroglia, okay, are support cells, and they are vast in number. Neuroglia are huge in number. Okay, they divide a lot, and they have a variety of functions, right? So here are the glia, okay, and quickly their functions, right? So you got astrocytes, okay. Astrocytes do a variety of functions, okay, various functions. They clean up around neurons, okay. They're important to form the blood-brain barrier. They don't form the blood-brain barrier. They help form the blood-brain barrier. Okay, so please understand. So variety of functions. Okay, so they help form the blood-brain barrier, not Better Business Bureau. Blood-brain barrier, BBB, BQ. Okay, so they form the blood-brain barrier. I'm going to see what that is next class. And astrocytes clean up the environment, which is very, very important in the brain. Okay, so they clean up around the neurons, okay, in the spinal cord and the brain. Astro means astrology, star. They're star-shaped. Okay. They also store nutrients, so they provide nutrition. Okay, and they can also store neurotransmitters. Okay, important. And we'll see what those are. Those are chemicals released by neurons. Okay, and again, there's nothing astrocytes don't do. They are rich in gap junctions, which means. So what do gap junctions ensure? Communication, synchrony. They talk to each other, right?
Yes.
Synchrony. Okay, it's important. Everybody remembers what synchronization means? Working together, right? Hello?
Yes.
Yes.
Mm-hmm. No, there's synchrony. Okay, so synchrony. So they work together, and so that's what astrocytes do. Then you got microglia. Micro means small, glia means tiny. They provide fixed innate immunity. They go around swallowing infectious agents and damaged cells. Okay, so they provide immunity. Fixed means they're jailed. They cannot get out of the brain or the spinal cord. Are we clear? They're specialized. Okay. Fixed. Innate means non-specific. You're going to learn this the last 2 weeks of class. Innate means, and if you took microbiome, you already learned it. Innate means non-specific. Okay. If you're a bacterium, I'm going to shoot you. End of story. Good, bad, ugly, I don't care. Okay. So fixed innate immunity. And then we've got oligodendrocytes. Oligo means small. Dendro means branching. So what does oligodendrocytes mean?
Small branches.
Small branches, correct? So they're important for myelination of neurons. Myelination of neurons. And myelin are fatty coverings of the neuron. Okay? Neurons have fatty coverings around them. That's called myelin. Okay?
Yes.
So myelination are the fatty sheets, okay, around neurons. So oligodendrocytes are responsible for doing that. So you've got astrocytes, microglia, oligodendrocytes, and then ependymal cells. The word ependymal means blanket, okay, blanket, or a rug, right? The rug you put in your living room, right? Carpet, okay? So ependymal means carpet, basically. So ependymal cells, okay, they form the blood-brain barrier. Blood cannot go into the brain. Okay, weirdly enough. Okay, blood-brain barrier. Okay, mainly because if blood cells were to enter the brain, they're going to block the neurons from interacting with each other, right? They're going to be a nuisance. Okay, and so if blood seeps into the brain, one of the earliest signs of blood seepage into the brain is massive headaches and epilepsy, right? You're going to have all kinds of problems, right? Because the proteins in the cells are going to interfere with the neuronal communication circuitry, right? You don't want that. So it forms the blood-brain barrier. So what kind of junctions would you expect here? You want impermeable, right? So you want tight junctions here, okay? So they're rich in tight junctions. Do tight junctions provide strength?
Yes.
No.
No.
Tight junctions do not provide strength, okay? Anatomy should have taught you that. Tight junctions do not provide you strength, okay? They only provide you separation of the environment, okay? So it helps with filtration. Now, all four of these are what we call CNS, or the central nervous system. We're going to see what that is in a second. So your central nervous system. Any questions on these four? Yes.
Would you say tight junctions was?
Tight junctions and gap junctions are all protein complexes. They're made of proteins, okay? And what they do is they connect one cell to another. Okay? So gap junctions, for example, will connect like this. See? It's a hole, right? It's a gap. So the two cells can be, if you turn one cell on, the other cell turns on. Right? Because they share their environment. Am I making sense? They're sharing their cytoplasm. Tight junctions are not like that. Tight junctions are like this, right? So what will happen? Material here and material here are going to be completely different on top and bottom, right?
Yes.
Because you're putting a barrier, right? It's a barricade. Does that make sense? Everybody? So again, if you have not heard of something, and again, that's supposed to have been covered in 102. Yeah, I covered in 102. But if you don't know something, there's nothing wrong with it. Ask. Otherwise, I'm telling you, there's going to be a multitude of people who don't know it or they don't remember it. Okay? It's also possible. So these are cell-cell junctions. You're going to be seeing these throughout the semester in every organ because we're multicellular and things have to connect to each other, right?
Yes.
So gap junctions and tight junctions are cell-cell junctions. Okay? They connect one cell to another cell in different ways. Okay? Yeah.
So all of these are neuroglia, these 4 types, and they all, we can get cancers from all 4 types in general?
As far as I know, yes.
Okay.
Probably very little from oligodendrocytes, but
Hmm.
the astrocytoma is the most common. Okay. All right. So
Sorry, one more question. When the fix in microglia, what does the fix mean again?
it's jailed in the nervous system.
Oh,
Can't get out of there.
As
Okay.
opposed to the others, which.
So liver has fixed innate immunity. Lungs have fixed innate immunity, meaning these cells cannot get out of there.
Okay.
Your skin has fixed innate immunity also.
Okay. The innate immunities are specific to each
The cells
system.
the immune cells are jailed to that
Okay.
system. Yeah.
Okay.
Okay, so the last two, so you have 6. The last two are satellite cells. So these are the astrocytes of the PNS. Okay, peripheral nervous system. Peripheral nervous system. They do everything, right? They clean up the area, they store neurotransmitters, they provide nutrition. They're basically the mother cells, okay, for the neurons that are in the periphery, meaning outside the central nervous system. Okay, and then we have another scientist named Schwann cells. Okay, these are involved in myelination of peripheral neurons.
Sorry, cells are astrocytes. What again? Primary nervous system?
Peripheral nervous system.
Okay.
I'll write that here. Peripheral nervous system. Any questions on glia? Once I do the classification of the nervous system, you'll understand this much better. And that's what I'm doing next.
So
Any questions on these?
oligodendrocytes, they multi-myelinate axons, but Schwann cells are individual myelinated cells
Correct.
in the peripheral nerves.
Yeah, but you don't need to know that detail.
Okay.
So, nervous system classification. So if you look at the nervous system, there are many branches. And this is going to be a little bit different than what you've learned in bio, if you learned it in bio. Okay, so when you look at the nervous system, we've got 2 major divisions. 2 major divisions, right? So you've got the central nervous system. Central nervous system. And you've got the peripheral nervous system. So one is abbreviated CNS and one's abbreviated PNS. So central nervous system is easy. It's brain and the spinal cord. Now, if you think of the central axis of the body, the vertical axis of the body, starting from your head all the way to your tail, that central axis, notice that the central nervous system lies along the central axis of the body, correct?
Yes.
Also, the central nervous system is the CPU of our computer. If your body was a computer, the central nervous system is the central processing unit. So functionally and anatomically, central nervous system is a very appropriate name. Okay? But that's it, no more divisions to the CNS. Peripheral nervous system has many divisions. So you've got 3 major divisions. You've got enteric nervous system, and enteric is dedicated to the GI tract. The GI tract is 21 feet long in all of us, 21 feet long. And so there's a dedicated nervous system for this GI tract. Are we clear?
Mhm.
You need it, okay? And so enteric nervous system, so this is basically your gastrointestinal tract. Some people will classify enteric as a separate division. Not wrong, but I feel like it's part of the peripheral nervous system. It's not inside the CNS. And peripheral nervous system is also composed of sensory neurons and a very important motor division. So sensory will sense stimuli, correct? It reads and senses and gauges stimuli. A motor is your response division. So to make it poetic, so sensory is the receptive division. Okay, motor is the response division. 2 R's. Believe it or not, making these rhyme or making them start with the same letter has an effect. Okay, making it easier for students to learn. I mean, not a huge improvement, but the scores did improve 2 to 3 points on each exam when this was done versus it wasn't done. Okay, so motor response is classified into 2. Okay, you've got autonomic and somatic. So somatic innervates skeletal muscles. Very simple. It's important for movement and force generation. Skeletal movement, skeletal muscle. Okay, motor means moving, right?
Mm-hmm.
So somatic nervous system innervates skeletal muscle, and autonomic is made up of 2 divisions. Your sympathetic nervous system, and this is your fight or flight division. Okay, you have a threat to life. Okay, and your life is threatened, your survival is threatened. The sympathetic gets turned on. Okay, or parasympathetic, rest and digest. So sympathetic, again, is fight or flight. Okay, you're dealing with adrenaline, right? Epinephrine, those type of compounds. They're both the same. Parasympathetic is rest and digest. And we'll go over these in another lecture. Classification of the nervous system. If you don't have any questions, study it right now. I'm giving you like a minute.
Why doesn't the central nervous system have so many divisions the way the peripheral does?
Because it's a processing unit. Its complexity comes into play when you look at the kind of stimuli it has to process. So if you're going to make this, and again, I'm completely blowing hot air here, but I'm pretty sure that it makes sense, right? Because if you want to evolve a major processing unit, okay? So let's say that you have a cashier of a bank. The last thing you want to do to her is burden her with all kinds of extraneous work, right? Because she's going to make a mistake counting cash. Well, of course, now we have machines that do it. But I'm just saying, right, it's a really important post. You don't want to burden them with anything else, right? It's that kind of an idea. Because it has to deal with such complex stimuli, you don't want further divisions of the central nervous system. And pure speculation. That's pure speculation. Okay, any other questions? Okay, so this is the sort of outline for the nervous system. So I'm going to go into structure of the neuron. Okay, very important. Okay. So the neuron is usually a single cell. Okay, that can be up to 2 meters long. It can run from your head to toe, right? But only be a single cell. Okay, so it's comprised of what's called a cell body. It's composed of cell body. Okay, and the cell body is also called soma. Okay, and branches called dendrites, okay, an unbranched axon, okay, and a branched axon terminal. So I'm going to draw what this looks like, and there are multiple types. We've got pseudo-unipolar, meaning it's not really unipolar, but it looks unipolar, okay? And then you've got bipolar neurons, and you have a multipolar neuron. Bipolar neuron means it has one dendrite, only one dendrite, and one axon. So it has two branches, right? Yes, and one cell body. So it kind of, so pseudo-unipolar looks like this, right? That's pseudo-unipolar. And it's usually very, very, very long, okay? Very long, because it goes to most of the skin receptors, are pseudo-unipolar receptors. Are we clear?
Yes.
Bipolar is very short, okay? So you have your cell body, and then you have one major and another major extension. So these are bipolar neurons. Multipolar is really easy, okay? So you've got all kinds of branches, okay? And then you have an axon terminal. Pseudo-unipolar neurons are exclusively sensory. Majority of bipolar neurons are also sensory because they're found in the eye and the nose. Multipolar neurons are not so, okay? Multipolar neurons can be sensory or motor, okay? Majority of neurons in the body are multipolar. Any questions on the types? Okay. So we're going to look at the structure of a multipolar neuron. That's what we're going to use as an example, okay, for neuron structure. So you've got a multipolar neuron, right? So you can kind of draw it like this. Okay, so draw. So this is sort of what it looks like. The nucleus is very obvious, okay? And what's interesting is multipolar neurons have a lot of branching, okay? Okay, at all edges. And I've recently seen videos on Facebook, very interestingly, where they've taken these stem cells and they differentiated them, and the first things these cells do is they branch out and try to connect with other neurons. Okay? So what are the parts? These are your dendrites. And the dendrites, their main job, like I said before, is reception. They receive signals. Or they receive stimuli. So what kind of, tell me, what kind of potentials will they exert? Greater potentials, okay, good. So dendrites primarily generate greater potentials, good job, okay. And then this is what we call your cell body, or soma, okay. And what is interesting is you have a little mound here, like a little hillock, and that's exactly what it's called, okay? It's called an axon hillock, meaning it's a small hill. And the significance of axon hillock is this is where the first voltage-gated sodium channels occur. Right? So let me ask you this: where do action potentials begin? Axon hillock. Okay. And then the so then you have this myelin, okay, right here, placed here by the oligodendrocytes, okay, in yellow. So this entire portion, okay, is called the axon. And these gaps here, these are unmyelinated parts. And they're called nodes of Ranvier. Okay, French guy. Nodes of Ranvier. And the membrane, people, this is what they say. They call the nodes of Ranvier the naked portions of the neuron. Naked. Because they don't have the fat around them. They don't wrap the fat around them. So what would happen if you wrapped fat around nodes of Ranvier? Those are your only gaps, correct? So if they get filled with fat, then the current will not move. Make sense?
Yes.
Current cannot move through fat, right? So if the nodes of Ranvier were closed, the action potential would not propagate. So you need these to propagate action potentials. And inside the cell, you have vesicles containing neurotransmitters. Okay? Ideally, each neuron can only release one neurotransmitter, one or two neurotransmitters maximum. Okay? Beyond that, it becomes very confusing. Questions? Anyone? Everybody okay? All right, 5-minute break. Be back around, be back. Change to how it's administered. You don't need a Scantron. The exam will be on Canvas. All your lab exams will be on Canvas. So you will need your laptop, okay? And you will need locked-up browser, but it will be on Canvas. And it will be held in person in the lab. So please make sure that you're here. I cannot allow you to take it outside. I have to proctor you. So, so lab exam will be followed by lecture exam, right? The week after, right? That will cover up to and including the end of nervous system. And trust me, you want it like that. Because otherwise, if I were to test you on just action potentials and cell transport, you'll get the toughest questions, and you want the nervous system to kind of buffer that, okay, the hard topic. So ideally, every unit exam will have 2 chapters, okay? So you do need to keep up with it, and this week is, or this coming holiday on Monday is perfect, right, to help you catch up with all this material. So use this week to catch up, and I'll give you a list of topics that will go into your next exam. I've started writing that exam. So I'm going to give you a list of topics that's going to go into it. I wanted to gauge how much I will get covered today and Thursday, okay, and based on that, give you an idea of what's on the lecture exam. Lab exam will cover PhysioX, right? PhysioX1 and PhysioX3, and it will cover the labs we have done physically in the lab session. Today the tutor was able to record, thank you Ishan, a nice video of EEG. So I'll post that for everybody to watch. Okay, so please watch it before you come on Thursday. Okay, students were able to finish an hour ahead actually, so it wasn't too bad. What else in terms of announcement? Yeah, no, that's it. Okay. All right, so let's jump right into this. Okay, so let's look at neuron structure a little bit more. Okay. So neurons contain cell bodies. Okay. The cell body or the soma is the most important part of the neuron. Okay, so this is where most biochemical activity happens. Okay. Put this on both ends. Okay. So please don't make that noise. Yay. Okay, it's just my noise. All right. So cell body is the primary site of biochemistry. This is where all biochemical reactions of the neuron happen. It's like the brain of the neuron, right? Everything happens here. Okay. So the cell body of the neuron is almost all biochemical activity. So almost all biochemistry happens here. All reactions happen here mainly. Okay. Okay. And the cell body for most neurons, it lacks centrioles. And this is the reason neurons cannot divide, because they don't have centrioles. If you don't have centrioles, remember mitosis, you can't form spindle fibers and you can't segregate chromosomes, right? So neurons fail to divide because they've lost their centrioles. Okay? So most neural cell bodies, there are some exceptions, but the general rule is they don't have centrioles. And most importantly, your neurotransmitters are synthesized here. We make your neurotransmitters here. Neurotransmitters are chemicals. They are chemicals. If you've ever had MSG in your food, that's a neurotransmitter. Glutamate is your neurotransmitter, okay? And it enhances taste, right? That's why you use MSG in most typically Asian food. But glutamate is also a very important neurotransmitter in the brain. So if you use MSG daily, okay, people will go blind. It will cause blindness. It's not good for you. Okay? So of course I'm talking fairly high levels, okay? Because MSG does get stored in the body. We have a way to store glutamate, okay? Everybody heard of dope, right? Dopamine. Dopamine is a neurotransmitter. Adrenaline, that's a neurotransmitter. It's also a hormone, but it's also a neurotransmitter. What else? ATP is a neurotransmitter, believe it or not. You've heard of ATP as an energy source, right? ATP is a neurotransmitter. Okay, so important. Anyway, the good thing is we're not going to memorize the neurotransmitter table. Okay, I have a feeling I may have gone over this in the video, but you do not need to know neurotransmitter table if it's there. Are we clear? Do not, absolutely will not ask it. It's pointless. Okay, you don't need to memorize it. So neurotransmitters are made in the cell body. Most importantly, cell bodies are the reception centers of the neuron. They receive messages. Now, everybody's seen a relay race, right? You take a stick, you run, you pass it on to the next person, right?
Yeah.
That's how the nervous system works in us, right? One neuron will release chemicals, which will stimulate the next neuron, and that will get stimulated. It will release neurotransmitters. That will stimulate the next, except this is happening in a million to a million to a million way in the brain. Okay, it's not 1 to 1 to 1, right? Just imagine, right? Just imagine, very simple, right? I come to class smelling of vanilla, right? In one person, what is that going to do? Like for me, I can't stand vanilla, right? So I'm going to smell the vanilla and go, oh, so nasty, right? Reminds me of my ex-girlfriend, the baker, right? I hate this. Why am I here? That's it. I'm going home. I'm going to be an economics major, right? So that's one response. What's another response? Oh my gosh, my grandma used to make this vanilla bun cake, and it's amazing. And I just love the smell. Oh, grandma, I'm going home. Either way, it's all going home, right? So you know what I want to do right now. So the bottom line is, how come one little stimulus can evoke so many different responses? And in the same person, again, I'm going to do this mainly to break stereotypes, okay? So if you wake up a man at 3:30 in the morning, right? And, and you basically show him something, right? That is actually pleasant, right? I wake him up and I go, here's a beautiful flower, right? He's gonna have plenty of select words, correct? Where is he, Sean? Plenty of select words, right? So the same guy, right, at 1 p.m., right after lunch, right, you show him this picture of this flower. Much different response, right? And I'll give you a realistic example, right? And this is really important to understand because this is part of physiology. You can see this in smokers. I'm talking typical cigarette smokers, right? And it's way more enhanced and exaggerated in e-smokers. Okay? By the way, e-smoking causes pneumonia, it causes lung damage, and it causes bye-bye time by the time you're 30. Okay? So of course it doesn't cause cancer. You don't live long enough for it to cause cancer. So I'm talking regular smoking. My dad smoked like a chimney, right? And very quickly I learned that report card signing or truancy signing, I always got into trouble. So when parents sign off on truancy, right, our school used to write notes and send them to parents, and parents had to sign it. And I always got into enough trouble so they wouldn't call my parents, right? But I'll get notes, right? And if I showed it to my mother, I'm done. Okay, she'll pull the, her wonderful version of the chancla, the spatula, right? The traditional Indian spatula. You do not want that thing on your ass, okay? So what I would do is I would wait till my dad stepped out of the house, had a smoke. He'd walk in. I'd be like, "Oh, Dad, I have something for you to sign." And he knows it's truancy. If I had shown him that before the smoke, right before the smoke, I don't think I'd live long enough to even worry about this, right? But right after the smoke, he's like, kids will be kids. And if I wanted something, that's the time I'd ask him. Okay? What's in cigarette? Nicotine. Right? What does nicotine do? It stimulates your parasympathetic nervous system. And parasympathetic is what?
Rest
Hello,
and
good morning.
digest.
Rest and digest. My dad is all chill, right? And he's able to think very, flower at 1 p.m., right? So why did I give that example? Anybody, you wake them up at 3:30 in the morning and show them a flower, they're going to beat you, okay? But men in particular undergo PMS at 3:30 in the morning. I could have easily used a woman's example, right? Saying if she's going through her periods and you show her something irritating, she's going to beat you, right? I don't want to do that because I want you to know that men cycle as well. And men go through the same, and it's even more exaggerated when men don't sleep. It becomes worse. It starts at 3:30 and lasts all day, okay? They're irritable because of that, right? Unfortunately, people think, oh, he didn't have enough sleep, right? Whereas for a woman, what happens? Oh, must be those days. Okay? Don't ever say anything stupid like that again in your life. Men, okay? Don't ever say that because you cycle too, okay? And, evolution made sure that your stupid ass is not awake when it's going through it. Women can handle that with grace. Men can't. Okay? So as you can tell, I was the president of the feminist club in that direction. Of course, I signed up because I liked the girls there, and then I started believing it. Why else would I be in a frat and be in a feminist club? And then I really started buying into everything they were saying. I mean, it's true. 99% of stereotypes, right, are true. And I felt bad for women, and I said, you know what? I'm gonna stand for this. It's something I believe in now. So, nature never discriminates. Nature never discriminates. Women go through PMS days, men go through PMS days. Go tell your dads that. Okay. So, and grandpas. Okay. So, reception center of the neuron. Okay, back to the point. What happens here? The point I'm trying to make is the same stimulus, the same exact picture of the flower, okay, in a man or a woman going through PMS symptoms versus non-PMS symptoms elicits a very different response. A male rat, when he approaches a female rat right 2 days before she's ovulating, okay, she will lick him and groom him and she's all friends with him and, oh, you're my best friend. He tries to pull that trick, okay, 3 days after she ovulates, she will bite his head off. She won't eat him. Rats don't cannibalize. Mice cannibalize, right? Rats don't. But she will bite his head off. And if he tries to pull that stunt when she's pregnant, forget it. Okay? She becomes so violent. She has more androgens than he can even dream. Okay? Androgen levels spike. Go near a cow who's just given birth. She'll gore you to death. A gentle cow. Because the androgen levels are out the roof. It's all hormonal. Do you understand that?
Yes.
So don't ever say, she crazy. Okay? She ain't. It's hormones. Absolutely hormones. Okay? And it's very important to get educated. Both men and women need to be educated about this. Women, because you need to know how your body works. And educate all your children. Women educate children, most part, right? And men, you need to stop being idiots and know this. Okay? So, reception centers of the neuron. What did I tell you? Whenever you receive stimuli, right, you get the same stimulus can cause a variety of responses, right? Okay? So the circuitry is really complicated. And it's not just circuitry. Think about it. If it's just circuitry in the brain, why the hell are you responding so differently from 3:30 in the morning to 1 o'clock in the afternoon? Before lunch, after lunch, you'll find a completely different me, right? And before smoking and after smoking, my dad, right? Because the nicotine calmed him all down and he's all happy. And before his smoke, he's all irritated because he's feeling withdrawal, correct? Am I making sense here?
Yes.
So all that plays into, so it's a very complex idea. What is? The physical circuitry makes a difference. Okay? How the neurons are all connected physically makes a difference. How they're connected chemically makes a difference. Okay? During PMS days, your neurons release a different set of neurotransmitters. And during fertility days, you release a very entirely different set of neurotransmitters. Make sense? When you take a rat, and a rat is really, if you grab a pregnant rat, there's a way to grab a pregnant rat. I ran a rat colony for 8 years for Berkeley, so that's how I know. I did all my research with rats. And rats are lovely creatures, okay, lab rats. They really, you want to see loyalty and you want to see love and affection, they can beat a dog to it, okay? They're that loving, okay? I've seen them cry when they missed me, when I didn't show up for a week. Okay, mice are cannibals. Mice are disgusting creatures. They should be wiped out of this planet. But rats are amazing creatures, right? So I've grabbed pregnant rats right before their labor, and I would pet them. And when you pet them, they become so calm, okay? And their labor goes so well. Okay, it is a proven fact. I mean, so all this behavior changes happens because of how the cell body receives the signal. And what signal it receives, correct? So the circuitry is complicated physically and chemically. Please, for heaven's sake, write this down. Neural circuitry is extremely complicated on 3 levels. Physically, chemically, and here's a really important word, temporally. Physically, chemically, and temporally. Okay? Major regulation here. Temporal means time. Okay? Depends on the time. And not the time as in the clock. I'm talking about the developmental stage of the neuron. Right? And your own developmental stage. Before puberty, after puberty. Lots of things vary. So the cell body is the reception center. Is that making sense?
Yes.
Okay. So if cell body is the reception center, what kind of potentials would you expect here? Reception center. What potentials?
Graded.
Graded.
Graded potentials. Very good. Graded potentials. So very, very crucial. I'm going to write it in red. Graded potentials occur here. Is that all or none?
No.
Okay, good. Graded potentials occur here. I'm even going to highlight it. Okay. Now, if these graded potentials are strong enough, okay, they will make the axon generate action potentials. So the junction of the cell body and the axon is what we call the axon hillock. And why is the axon hillock important? The axon hillock is where voltage gated, your best friend, sodium channels show up here. Will you find them on the cell body? No. The first place they show up is that junction between the cell body and the axon. Are we clear?
Yes.
Yes.
Which means action potentials will only occur at the axon hillock. Are we clear?
Yes.
So just to draw this as a cartoon. So here's your cell body, correct? And I'm going to draw the axon hillock in red. Yes, everybody see that?
Yes.
And then we have the axon here, right? And here's your axon terminal. Everybody got that?
Mm-hmm.
The stick figure of a neuron. It's a very important diagram, okay? So I'll blow it up in a minute. So you got stimuli, right? So what kind of potentials happen here? Graded potentials happen here, correct?
Yes.
Yeah.
Yes.
So if the graded potentials are strong enough, what will they do? So I'm going to say question mark, right? Why? Because you're going to have a weak signal there, right?
Mm-hmm.
If they're strong enough, you open, again, the red is axon hillock, right? If they're strong enough, what will you do? You generate an action potential, and that gets propagated down the axon. Are we clear?
Yes.
Extremely important diagram. And we're going to learn exactly how, because we know exactly how. It's an amazing piece of physiology. And at the axon terminal, which can be branched, okay, so this is your axon terminal. This is where the neurotransmitters are released. I want everyone to draw this and tell me if they're following. Here's another example of how the graded potential can give rise to an action potential, right? Good morning. So, I do want to very quickly introduce neurotransmitters to you, okay? But before I do that, I want to wrap this up with another important fact, okay? So, the number of dendrites, okay? If you have only 1 or 2 dendrites versus you have 150,000 dendrites, right? Tell me, which one's going to be more sensitive, 150,000 or 2?
2.
150,000. The more dendrites you got, the more sensitive you'll be, right?
Oh yeah.
Think of the surface area. Yes?
Yes.
So let's say, this is a horrible example, but that's all I can think of. Let's say that you have, really long spiky hair, right? Let's say your hair can conduct electricity, right? If you have 150,000 spikes of hair, right, versus I only have one hair, and lightning strikes. Guess who's royally screwed, right? The 150,000, okay? The bald man escapes. Am I making sense?
Yeah.
Yes.
That kind of an idea. So remember that number of dendrites determines the sensitivity. So the greater the number of dendrites, okay, the greater the sensitivity because of surface area. And I do want to mention, start this off and then we'll continue this on Thursday. Neurotransmitter action. Okay, neurotransmitters are chemicals released by neurons. Okay, so neurotransmitters. Again, if there's a table in the video, ignore it. Okay, you don't need it. Neurotransmitters are chemical signals. I should say chemical messages. Okay, released by neurons. Okay, primarily for the process of communication. Okay, and neurotransmitters can be divided into two. So there are two types. Okay, and they're very easy classification. You're either an excitatory neurotransmitter or an inhibitory neurotransmitter. There's no such thing as neutral neurotransmitter. You're either excitatory or inhibitory. Think about it. Excitatory means, okay, you will generate, of course, you will generate a graded potential dipole, okay, which then leads to an action potential in the target, okay? So what would inhibitory be?
Generate a hypo.
Thank you, hyperpolarization. Okay, will there be an action potential?
No.
No, hyperpolarization doesn't lead to action potential. The signal stops there. This helps us prevent abusing of the nervous system. How many of you have seen this? If you give a frog any kind of stimulus, right? You've seen how frogs react, right? For anything and everything, they just jump.
Yes.
Their entire body jumps, even after they're dead, right? If you give them a small bolt of electricity, their whole body will jump, right? Because they have electrical synapses. All their neurons are connected. So if you excite one neuron, everything gets excited. Am I making sense? Isn't that abusing the system? This is why amphibians don't live long.
Oh.
Starting with reptiles, with what happened in evolution, reptiles disconnected their neurons. Hello, look at how long turtles live. And snakes certainly live longer than fishes and amphibians, right? Because they were able to disconnect their neurons and use chemicals and only transmit those signals to the brain that are worth it. Look at how much noise you are saving. Look at how much energy you are saving. It's that many less action potentials you're generating, right? Okay, so inhibitory neurotransmitters are extremely important. Are we clear?
Yes.
Very, very lasting, and I'll let you go. Very, very important example, okay? Why am I on walking mode? Stupid watch. I didn't move for an hour and a half. Okay, so everybody, so you know about Parkinson's, correct? And what happens in Parkinson's? They're tremoring all the time, correct? So normally, why am I not tremoring, right? And usually with age, people do tremor, right? But usually it's a little bit in control. Parkinson's is a degenerative disease. As time goes on, it gets worse and worse, right? The brain uses dopamine. The brain uses dopamine, okay, to make sure that many of the motor neurons are silenced. So my body stays still. And if I want to move my finger, I only move my finger. Am I making sense?
Yes.
And I can bring it back to rest and sit calmly, correct? So what's happening with tremors? These people have a dopamine deficiency, correct? And so it's called substantia nigra, or black substance, and they run out of it, right? And they cannot produce this, and so their neurons are constantly excited. Everybody see that?
Mm-hmm.
So inhibitory signals are extremely important. Are we clear?
Yes.
To keep us in balance. Just to give you an idea, because you might think, who uses inhibitory signals? We do. Okay? So when we come back Thursday, I want to talk about neurotransmitter action. Okay, we're going to talk about that, and we're going to talk about this excitatory, inhibitory just a little bit more. Okay? And then neurotransmitter action, and then on to the brain. Okay? All right. Have a good Wednesday. I'll see you all on Thursday. Okay?